Canlı gönülden söylüyorum.
Okay, let's continue with our conventional many-body systems. Okay, so we were also looking at multi-particle systems. Well, this was basically a generalization of what we had done for two particles. And okay. Now, one of the problem is, for example, if you look at a realistic system, even I don't know, some of the protein molecules you have, they have hundreds, if not thousands, of electrons. If you try to solve all of them, the wave function of all 1,000 electrons, or I don't know, if you have a macroscopic object that's an Avogadro numbers of electrons, that's kind of tough. Now, to deal with such systems, okay, one is you will study, or you have already studied, statistical mechanics. That basically deals with trying to avoid solutions of the quantum mechanical problem of Avogadro numbers of particles. Now, there are other approaches. One is the so-called density functional theory. Well, this is especially used to study molecules. Now, if you would like to use statistical mechanics, you need a huge number of particles, much more than what you have in actual molecules. So that's where this density functional theory also comes into the game. Now, one observation is that do we really need to know the wave function of the system? Well, the answer most of the time is no, we don't really care about the wave function. We need to know the energy eigenvalues most of the time. And in fact, that statistical mechanics basically just tries to determine properties of your system only using the allowed energy eigenvalues. That's it. Now, in density functional theory, the first claim is, let's say we have our wave function. Of course, this should be symmetric or anti-symmetric under the exchange of any two. Well, I'm not writing down those explicitly, but just think of these positions as R1 and R2 as both the positions and all the other degrees of freedom your particle can have. For example, for the electron, R1 represents its position and the spin. And the wave function has to be anti-symmetric for electrons and symmetric for bosons, yes?
Should it only be anti-symmetric under the exchange of 1, 2, or can it be like anti-symmetric under 1, 2, and 6, 7?
Anti-symmetric under the exchange of any two of them. So if you make two, let's say you change 1 and 2 and 5 and 6, well, if you change 1 or 2, it acquired a minus sign. You change 5 and 6, it acquired another minus sign, so the wave function didn't change.
So a triplet, maybe? 1, 2, 5, 6,
Yes.
8, 9.
Well, for each exchange, you get a minus sign. Just think of it like that.
So it can happen?
Sure. It has to be symmetric or anti-symmetric under the exchange of any pair. Now, if you want to make I don't know, exchanges of 5 pairs, then it's minus 1 to the 5, because each pair will bring a minus sign.
Hocam başına ikisi artı mı yazdınız?
Plus or minus?
Eksi mi yazdınız?
No, that's plus or minus, depending on the kind of particle you have.
I believe he is saying that can 1 and 2 exchange be negative sign and 5 and 6 exchange be positive sign?
Are they identical particles?
Do we have to take care of identical particles only in density function?
No, if
No.
5, 6 doesn't change the sign, then under the exchange it will get a minus sign. So, but these two are still symmetric because it doesn't change the sign. So it needs to be either 1, 3, 5 exchanges or something. It should be all exchanges.
So it can happen, right?
Sure. No, I mean, you see. If this is what you are asking, so I have two exchanges. and the sign didn't change. But since we are talking about identical particles, so if it changes sign under the exchange of R1 and R2, it should also change sign under the exchange of R5 and R6. They have the same properties.
Yeah, so if I changed one more, R9 and R8 too, then it's
No.
anti-symmetric.
A minus sign for any exchange of pairs
But we can
for fermions.
we can describe density functional theory for non-identical matrix also.
You see, I didn't yet do density functional theory. I'm just looking at identical particles, and the problem I'm interested in is basically the electrons in the molecule, which are identical particles. I don't even look at the nuclei, because usually what is done is the nuclei are very heavy, so what you assume is you solve the electrons assuming some position of the nuclei fixed, and then you change the positions of the nuclei and see if you minimize what is the minimum energy configuration. But when you are solving for the wave function of the electron, you always assume the nuclei to be at rest at given positions.
So if we change 1 and 2 and then 2 and 3rd,
How many exchange?
two exchanges?
It is
or
two.
one exchange?
Well, it is two exchanges.
But at last we only change 1 and 3.
Well, let's see. What you are saying is first you exchange 1 and 2, right? Then you exchange 2 and 3.
The second and 3 and the third.
The second and the third. Okay, so this is minus. This is not just a single, sorry, this is plus. This is not just a single exchange.
Is order important? I guess not.
Well, I mean, consider the exchanges. What do you mean by order important?
First 1 and 2, second and third.
So what is the exchanges you want to ask me? You define which exchanges you are carrying out. So she told me that first exchange 1 and 2, then exchange 1 and 3. That is what she told me, right?
Okay, if we do first 1 and 3, then 1 and 2.
So you say if we do 1 and 3 first, and then 1 and, which one? 1 and 2.
1 and 2.
Şu an tam şey yapamam.
Okay, fine, the result is the same. So
Yes.
what's the problem?
Why are we talking about the order?
I don't know, you asked for the order. I didn't.
I mean, the pair change, the number of the pair change is the only important thing.
Yeah. So
I was trying to create a scenario where you make two exchanges, but at the last picture, when you compare the initial one, there is only one thing that...
it doesn't exist. You see, there is a property called the signature of permutations. You see, if you look at any permutation that you can imagine, for example, let's say 1, 2, 5. Now, this is a notation of a permutation. What it does is it maps 1 to 2, 2 to 5, and 5 to 1. I can write this as 1, 2, 1, 5, right? No. 1, 5, 1, 2. So 1 is mapped to 2, and this thing doesn't do anything with 2. So 1 is mapped to 2 in this 2 permutations. 2 is mapped to 1, which is mapped then to 5. So 2 is mapped to 5. So this doesn't do anything to 5. This maps 5 to 1. I can write the same permutation as 1, 5, 1, 3, 3, 1, 1, 2. Well, this is kind of trivial. Because 1, 3, 3, 1, this product is just identity. It's the same permutation. So given a permutation, you can write it in infinitely many ways. containing many different numbers of pairs of permutations. The only thing that doesn't change is whether the number of pair permutations in this expansion is either always even or always odd. So you cannot just write a permutation in terms of 2 exchanges and also 5 exchanges. That doesn't happen. So in the signature, that's called the signature of the permutation, it is always fixed. And this sign over here is basically the signature of the permutation that takes you from this one to this one. Now, any questions? Let's go back to I still didn't do any density functional theory yet. Let me define the density so that I can talk about the density functional. Well, if you have, let's say, n particles and point particles, the density of each one of them will be a Dirac delta. This is a point particle, which basically means it's the number density. So if you integrate it over in a region containing the particle, it gives 1. If you integrate it over a volume that doesn't contain Ri, it will be 0. That's basically the definition of the density. Well, I have many particles, so let me just sum them up. This is, let me call this the density operator at the point R. Now, the density is the expectation value of this one. Which will be Rn psi R1, R2, Rn psi star to Dirac delta, R minus Ri, and psi R1 to Rn, sum over I. Now, what I will have here is let me write it in this form. You see, that Dirac delta, I can use that Dirac delta for each one of those i's to mean, now let me use a j, to evaluate the Ri integral. So I will evaluate all the coordinates remain the same, Ri, except then one of them is now R. I just use this one to evaluate the Ri integral. This is all the integrals except then the ith integral. Here in this wave function, I replaced Ri with R. That's the only thing I did. Well, now what I can do is this will be psi star R, R1, Rn squared. I just move that R to all the way to the front, just exchanging them. Well, at each exchange, I get a plus or minus sign, but since I'm taking the absolute squared, whether I take a plus sign or a minus sign, it doesn't really matter. Now I can just, you see, there are these n minus 1 dummy variables in each one of those terms. I can just rename them. No, because I evaluated one integral. Yes. Then this is R2, R3, Rn psi. I'm already taking the absolute value. This is what I call n of R. Let me also write this. Well, you see, all of these terms are the same. It doesn't depend on I anymore. This is just n. This is what I call the density of particles. And if you evaluate over R,
It shouldn't be to the power n.
hmm?
It shouldn't be to the power n.
Why?
I have these nested integrals. They all have different integration variables, but they'll get multiplied with each other.
I'm not evaluating that integral. That integral stays as it is.
Why it's not n minus 1?
Why should it be n minus 1? Because I mean,
We said that we have n minus 1.
okay, but you see, this is from the definition of the density. The density is a Dirac delta at the position of each one of those particles. I have n minus 1 variable, so here I have 3 times n minus 1 dimensional integral. I'm integrating over not the first argument of psi star psi squared, but I'm integrating all the remaining arguments. That is what I call the density at the position x. And if you integrate over the r, well, that is just an n times the normalization of the wave function, which I will assume to be 1. Well, this is also what we expect. If we have the number density, you integrate the number density over all space, you should get the total number of particles.
Where did we go from psi star to psi?
Well, psi star squared is psi squared. Since I'm looking at the absolute value, it doesn't matter. Now, we have our Hamiltonian, let's say. The Hamiltonian will be the kinetic energy of all these particles, plus some pair interaction of all the particles, plus some external potential, external to the electrons. And they will be usually, this will be it can be, for example, you have, if you consider a solid state, all the electrons, you are looking for the Hamiltonian of all the electrons. The nuclei are positive charges. Those positive charges will attract the electrons. So that is the external potential over there in that example. And typically what you want to do is the system will be in the ground state. Look at the some expectation values in the ground state. Let's say, what is the expectation value of this one? Let's try to calculate it in the full theory, using the full wave function. Well, you see, if you look at all these derivations over here, there will be only one thing that will change. I don't have a Dirac delta, so I won't be able to evaluate that integral. That integral will still remain. But all the other steps will be almost identical. So this will be sum over I d cubed r1 d cubed rn psi star r1 up to rn squared v external ri. Now I is just one of the 1 through n. Let me just rename all the variables, all the positions. Let's say that for I is equal to 5, here I have the external R5. Here I have psi star R1, psi R1, Rn squared. Let me just change the name R5 to R1. And so this if I change R5 to R1, I can just reorder all these so that let me change R5 to R. Reorder all these arguments of my wave function so that R is the first argument. All the rest, I can just rename them, rechange their order because the wave function is symmetric or anti-symmetric. Nothing changes. So this integral is actually d cubed r, d cubed r2, d cubed rn v external r psi of r r2 rn squared. I just renamed my variables and ordered the arguments of my psi so that the arguments are r, r2, r3, rn. But then I have the external r, then n times d cubed r2 squared. Well, this is nothing what I called as nr. So I can write this expectation value as, if I can calculate that expectation value if I know the density nr of my state. Typically, whatever you want to calculate the expectation value of, they will be just such sums over functions that depend on each one of those electrons. So most of them I can just write in terms of the density. So I don't need to know the wave function, but I need to know the density to evaluate these expectation values. So that is one observation. Now, if I know the wave function, the density is given uniquely. If you know the wave function, you know the density. Now, my claim, the first thing I will prove, if you know psi, then you know n. My next claim will be, if I know n, I know psi. So the relation between psi and n will be 1-to-1. If you know one of them, you know the other one. Again, the Hamiltonian. Now, to prove this, what I will do is, this is my Hamiltonian. Let me say that I have another Hamiltonian. Given by some different external potential. Now, the reasoning will follow this one. You see, V external, if I know the external potential, okay, well, let me take one step back. I'm looking at electrons. Those electrons can be, I don't know, in my keychain or in this marker. If the number of electrons is fixed, the interaction between the electrons is the same. The Hamiltonian the potential describing the electron-electron interactions, this one, will be the same. In these two problems, the only thing that will differ is the external potential the electrons will feel. So the external potential uniquely specifies my wave function. And if I know the wave function, I know the density. Now, what I will assume is there's another external potential which corresponds to another wave function. So this is a different system, another wave function. But let's say that it has the same density. I already know that if I know the wave function, I know the density. There's no other density that corresponds to that wave function. Now, what I would like to prove is if I know the density, there is no another system and another wave function that has the same density. So if I know the density, I know the wave function of the system. So usually such proofs go by contradiction. I just assume that it exists, such an alternative system with a different wave function having the density. Now let me look at this one. Psi prime H psi prime.
I couldn't understand. We can have a different wave function but same density?
I am assuming that I can have that. And then I will try to obtain a contradiction. And again, I am looking for the ground state. That is also something we should keep in mind. Now, since I'm looking at the ground state, this matrix element has to be larger than psi h psi, because this is a ground state of h. But remember, there is this this is equal to, let's say, psi prime h0 plus v pair psi prime plus psi prime v external psi prime. This should be larger than psi h0 plus the pair interactions psi plus psi v external psi. I'm just writing the h as h is equal to h0 plus the pair interaction of the electrons plus whatever external potential I have.
I have a question.
Yes?
We assume that psi is ground state,
Yes.
but we don't know psi prime
Yes.
state. Okay.
Yes, this is what I am
It
saying.
may be ground state.
What I am saying is, if I have the external potential V external, there is a corresponding ground state psi and the density n. If I have a different potential V external prime, it will have a different ground state psi prime. But the potential is different, it is not the ground state of the initial potential. It's some other state. Whatever the state is, the matrix element of the Hamiltonian should be always larger than the matrix, larger than or equal to the matrix element of the ground state. But since it's not the ground state, it's a different wave function. So it cannot be equal, it has to be larger.
Hocam, V extension, V extend, psi prime is not related, right?
External potential of V and external potential V prime, they are different.
No, yes, but why we are using psi prime and not primed?
Because here I'm looking at the matrix elements of the Hamiltonian of both sides. H, not H prime.
Okay.
H is this one. That
But
is my
we are
H.
Taking the product of unrelated two things, and why we are comparing this?
I'm not looking at two unrelated things. What I'm saying is I have an H, which is H0 plus V pair plus Vx. This is my H. I'm looking at this matrix element.
Okay, why?
Psi prime, we will come in a moment. I'm looking at this one and I know that this has to be larger than psi h psi. This is I know. Now what will this lead to? Well, we will see in a moment. Well, let's come to over here, this equation. It's the same h on both sides. So I have Vx on both sides, but remember, psi prime Vx psi prime is d cubed r Vx n r. Let me put the prime. This is the density corresponding to psi prime. But I made the assumption that they are the same. This is my assumption. So this one and this term, they are the same, those two matrix elements, since I am assuming that psi prime and psi, they are corresponding to the same density. Those two terms are the same, which tells me that psi prime H0 plus V pair, psi prime matrix element should be larger than psi H0 plus V pair, psi. Okay, this is one result I have.
So are you claiming that there is a map from set of wave functions to density functions?
Yes.
Which is one-to-one?
That is my claim.
And
You see, one way is already obvious over here. If you know the density, there is a one wave density. If you know the wave function, there is one density corresponding to that one. That one direction is obvious. What I'm trying to prove is that the other direction is also correct. And let me just finish my proof, and then you can ask your questions. Why did I look at the matrix element of H? Well, I can do the same exercise with H prime. Remember, H prime, let me look at this matrix element. Psi is not the ground state of H prime. Psi is the ground state of H, not H prime. Psi prime is the ground state of H prime. So I have this inequality. Well, I will basically do the same thing. Psi H0 plus V external, psi, no, not external, V pair, plus psi V external, psi. This should be larger than psi prime H0 plus V pair, psi prime, plus psi, sorry, you're right, there's a prime, external prime psi. These are primed. But since psi and psi prime, they have the same densities, that's our beginning assumption. These two are equal, so they cancel each other on both sides. So I have psi H0 plus V pair. This matrix element should be larger than psi prime H0 plus V pair, psi prime. You see, I have these two matrix elements. This tells me that this one is larger than this one. This tells me that, no, it's the other way around. So I have a contradiction. Which basically tells me that original assumption has to be wrong.
How did you write this?
Yes, because
Which one? This one.
yes, I thought it should be the opposite, not bigger than smaller.
You see, okay, if you have a Hamiltonian, you take the matrix element of that Hamiltonian, the expectation value of the Hamiltonian in an arbitrary state. That is larger than the expectation value of that Hamiltonian in the ground state. You see, H, Hamiltonian H has the ground state psi. So I looked at the matrix expectation value of H in psi prime. It should be larger than the expectation value of H in the ground state. So this is my initial equality, which led me to this equality over here. Then I looked at the matrix elements of H prime. And remember, psi prime is the ground state of H prime. Psi is some other state. So the expectation value of H prime in psi state should be larger than the expectation value of H prime in the psi prime state.
You follow the same analogy variational method. I remember that.
Well, this is the principle of the variational method, yes.
But the problem is, when we assume the trial wave function, we assume that that wave function was an eigenstate of that Hamiltonian.
No.
This time,
No,
we did.
no,
Because we're turning that trial wave function into an eigenstate, right?
no,
We are.
we are not.
I'm pretty sure we are. I'm pretty sure we are.
No, we are not.
Taking the eigenstate.
Well, what you're assuming is that you started with a trial wave function with a number of parameters. You minimize the expectation value of the Hamiltonian in that state with respect to those parameters. And you hope that the minimum energy is very close to the minimum energy eigenvalue, hopefully even overlap. And since the you minimize the energy, you are again approximating the ground state wave function with your trial wave function. It's an approximation.
But there's this thing, when I assume that when that operator acts on that state, it will result me in an eigenvalue. Doesn't it make it the eigenstate of that operator?
Approximately, yes.
So this time,
If you minimize it. But you say, I'm not minimizing anything here.
But then how can I tell that since psi prime shouldn't be the eigenstate of the Hamiltonian, I can't claim this identity holds?
I can always.
If I have this wave function for the ground state, I
Yes.
can always choose the trivial wave function, right?
Let's review the minimization. Okay. Variational method. What do you do in the variational method? You start with an arbitrary thing. This is arbitrary. You can always imagine expanding it in terms of eigenstates.
All right. Oh, I see. I remember.
Now, if you look at this matrix element turns out to be a n squared En, summed over all n, which is always, whatever the values of En are, larger than or equal to E0. I didn't do any minimization. Now, if I do minimization, if I insert some parameters if I assume some form of functional form for a n's, minimize this expectation value, etc., I hope to obtain the ground state, and I hope to obtain a wave function that is similar to the ground state. But even if I don't do the minimization, this identity is always valid. Whether you do the minimization or not is another issue, but that is always valid. In fact, this is the starting point of the minimization argument. So here I'm just using that argument. I have a system that is described by a Hamiltonian H, that is described as n electrons. There is this wave function psi prime of n electrons. I look at the matrix element of H in the psi prime state. I definitely know that this is larger than the wave function of H in the ground state. It is the psi state. I don't do any minimization, but whatever psi prime is, this is always true. Well, I'm saying that I'm also assuming that psi prime and psi are different. Now, that is my initial assumption. I started with, for a different external potential, it will give me a different wave function, but the same density. Then I said that since I am assuming the density to be equal, these two matrix elements, they are identical. So I can cancel them, and that gives me this relation between the matrix elements of H0 and this V pair. Then I do the same exercise, but instead of H, I use H prime. Now, psi is not the ground state of H prime. It has a different external potential. So the matrix element expectation value of H prime in this new psi state should be larger than the expectation value of H prime in the psi prime state, which is the ground state of H prime. But H prime also has this H0 plus V pair. That is a universal. For n electrons, V pair is just a pairwise interaction between the electrons. That's the same as long as you stick with the electron. And again, since the densities are equal, the second matrix elements of Vx prime, they are equal to each other. So I obtain the opposite inequality. Before I obtained one inequality, now I obtain the opposite inequality, which cannot be true. So my initial assumption that there exists a different psi prime corresponding to the same density, number density, should be wrong. So, which tells me that, okay, for each V, there is a psi, V external, But if I know the ground state, I know that means I know the external potential anyway. And if I know the wave function, I know the density, number density. And for each number density, there's a unique wave function. So basically, my system is described by this density, nr prime. So this basically shows me that that density nr prime contains all the information about my system. Now, the question of how can I extract useful information from this density is a different problem, which we will try to address. You see, in principle, this density, number density contains all the information that the wave function has, but extracting that information might not be easy. It is trivial in cases where whatever expectation value you try to calculate is just the sum of some operators that only depend on one of the particles. Then just multiply the density with that whatever operator you have, integrate over all the volume. But for example, if you have two particle interactions, two particle operators, then it's not so obvious. Well, there are also other not so obvious cases we will see in a moment. Questions?
Onu nasıl anlatacağım? Şimdi her Hamiltonian ve Hamiltonian prime'ın sadece bir external'ı farklı olarak tanımlıyoruz. H0 ve V pair aynı. Peki,
because H0 is basically the kinetic term, V pair is the pairwise interaction,
yani
electrostatic
bunlar
potential.
farklı olsa ve external aynı olsa yine aynı densilere sahip olan
No.
farklı şeyler.
That's a completely different problem. You see, here what I'm imagining is I'm looking at n electron systems. I have n electrons. They have their kinetic energy, which I call H0, or it would probably be better if I called it T. And there will be pairwise electrostatic potential between them. That is what I call V pair. Of course, these electrons will behave differently if I put them, I don't know, in a large molecule or in a box of volume V or, I don't know, a sphere. That is the external potential I have. They will behave differently depending on what external potential you have.
We know that the wave function has some time evolution. And
I'm looking at the ground state, so it's just a phase.
Okay, is there something like a continuity equation? Is there something like a continuity equation for the number density? Because all the examples that you give has some compact finite volume.
Sure. I mean, there should, in this case, the continuity equation, what will it be?
If there is no time dependence, then the divergent will.
Well, I mean, I'm sure there is a continuity equation, but I mean, what you will need is a flow of the number densities, but that means you have to introduce time dependence. Without time dependence, you don't have any flow, so the density doesn't change. So there's no point in talking about continuity equation.
What does this imply for the? Does this imply anything on the external potential?
No. I'm just except I'm being time independent. That's what we are assuming. I'm looking at the time independent problem. I'm looking at how a molecule just at rest over there what will be its ground state? What will be its shape in the ground state, for example? That's the kind of problems I'm trying to understand.
But in the case of if the external potential is time dependent, then can you say that the number density does not need to be constant with respect?
No, it doesn't have to be. Right. This definition of the number density, this one, this definition didn't assume whether psi is time dependent or not. So I can still make the same definition, but of course, as you said, in this case, the density will be time dependent. It will evolve in time. So in principle, you should be able to define a flow. You say there is a continuity equation for the probability density. This is basically the probability density itself, the number density, the probability density itself, summed over all the particles in a sense. And then if you look at the probability flow, that will be the current of the number density. So you have your continuity equation there. Okay, let's give our 10-minute break. And
Is it break or?
we can continue for 10 minutes. After 10 minutes, I will continue.
1 hour?
For 1 more hour.
For 1 more? What if we had other jobs because we changed the